Alright, so our next challenge here is actually to look at how do we determine the mass, the actual mass up here that we're going to use for our calculation. Now, to determine that mass up on top, let's assume here we have a sheet of paper. Okay, so we have a sheet of paper, and that paper sheet is 1 meter on the side, and so it's 1 square meter. So that paper sheet is 1 meter on a side, and we know the basis weight for this paper sheet in the units of grams per meter squared. So we know this particular relationship here. So we have 1 square meter of paper, and if we wanted to determine the mass of this paper, the mass is simply the basis weight times A, or the area. So this is the area. A is equal to the area of the paper sheet. Okay, so that determines the area of the paper sheet. Now, we would like to know what the total number of fibers that fall to make up this particular sheet of paper. So the number of fibers that fall are simply the basis weight times the area divided by the coarseness times the length of the fiber. And that gives us the total number of fibers that fall within that paper sheet. Now, more specifically, we would like to know something else. Now, we know this for the overall, but remember in the Poisson distribution, we need to know average values. So if we can determine the average, if we can determine the average number of fibers that fall in an inspection area, if we can determine that, then we can determine the variability in the basis weight. Alright, so let me explain. Our challenge here is we know that there's a direct relationship between the number of fibers within a given area and the basis weight. We would like to know how many fibers in total fall over this paper sheet to make up this paper sheet. We can calculate that right here. Okay, so we have our basis weight, the area of our paper sheet, and that gives us our number of fibers. Now, more importantly, we'd like to know something else. We would like to know, once we take this paper sheet and we carve it up into smaller sections, to be able to characterize its formation or the variability in its basis weight. So we're going to take this paper sheet and carve it up into these little square inspection areas. Okay, we would actually like to know how many fibers on average fall into this specific area. Well, the simplest way to do this is to determine how many total areas there are. Right, so if we broke this up, so that would be 10 down this side and 10 down this side, there'd be 100 total areas. If we know the total number of fibers, we just simply divide it by 100, and that gives us the number of fibers within that given area. That would be one way to do it. Now, another way to do it that's computationally more simple and straightforward is we can determine the number of fibers now for an inspection area. So this is the number of fibers for an inspection area. So this is our overall basis weight. So this is our overall basis weight of our paper sheet. And we simply multiply it by an area of inspection. Now that area of inspection is the area that we want to examine. So A sub I is the inspection area. This is a small part of the bigger sheet that we are examining. So now, if we take this basis weight and we multiply it by an inspection area, that gives us the average mass per inspection area. So if we know the average mass per inspection area, and we divide this number by the coarseness times the length of the fiber, this will give us the number of fibers within a given inspection area. Okay? We use a little bit different term for this because actually is what I'm trying to determine here is the number of fiber centers, right? So I'm going to give this the term C sub D bar, where C sub D bar is equal to the average fiber center density. When we work in statistics, whenever you see bar, that means the average of that variable. I call this center density. Right? Why do I use the term center density? I use this term because center density represents the number of fibers per inspection area. So the average center density we calculate like this above. So now we have the center density. This is the average number of fibers per inspection area, simply the basis weight, times the area of inspection divided by the coarseness times the length of the fiber. So now we know the average number of fiber centers, or for that matter, fibers within a given inspection area. Now once we know this average number, we can use that in the Poisson's distribution, right? So it's pretty straightforward. Once we know the Poisson's distribution, or we're going to assume that the Poisson's distribution applies here, if we know the average number of fibers that fall, we can also calculate the variability in the average number of fibers that fall. So there's a simple example problem that I could give you. Let me give you a example problem here. So let's start off here. We'll say a fiber has the following attributes. Fiber width equals 40 micrometers. Fiber length equals 3 millimeters. Fiber coarseness equals 200 milligrams per kilometer, and basis weight of the paper sheet is 10 grams per meter squared. So is what I'd like for you now to work through this and try to calculate what are the total number of fibers in 1 meter squared, 1 centimeter squared, and 1 millimeter squared. So take some time and work through that. Pause the video if you have to, and then come back to see how you would do that. Okay, hopefully you've taken a break and you've worked through this, and as what you've used was this particular formula up here. So let's use that formula, apply that formula. So we're going to say C sub D bar, and this is the total number of fibers, or the average number of fibers for that matter, in a given inspection area, and it's the basis weight times the area of inspection divided by the coarseness times the length of the fiber. So here we're trying to determine, I said, the total number of fibers in these given areas. So we don't know what they are for a particular sheet, but we can calculate the average values, or what the average values are, if we go around and look at these different inspection areas. So on average, we can determine the number of fiber centers within that given area. So let's say for a 1 meter squared area. So this is going to be fairly straightforward here. Before we get into any of this, it's always a good idea to put everything in a common set of units. So 200 milligrams per kilometer would be equal to 0.2 grams per kilometer, which would be equal to 0.2 times 10 to the minus 3 grams per meter. So now we have grams and meters there. Let's change our fiber length. And it's 3 millimeters now. We can say that's equal to 0.003 meters. Our grammage is okay, and we actually don't need our fiber width. That's an extra piece of information that we're not going to use. So let's plug this in for an inspection area of 1 meter squared. So C sub D is equal to 10 grams per meter squared times 1 meter squared divided by 0.2 times 10 to the minus 3 times 0.003 meters. You can work this through, and I think you should come up with a number that's on the order of 1.67 times 10 to the 7th fibers. Now if we used 1 centimeter squared, we have to convert this into square meters. So 1 centimeter squared is equal to 1 centimeter squared divided by 10,000 centimeters squared per meter squared. So that's equal to 1 times 10 to the minus 4th meters squared. So if we plug this in, we would get C sub bar D 10 grams per meter squared times 1 times 10 to the minus 4th meters squared over 0.2 times 10 to the minus 3. And I can put units on this. I should have put units on this before. These units are grams per meter times our fiber length of 0.003 meters. When we do go through these units, you see they all cancel out, and you end up with just a number on this side. So we've multiplied this by 10 to the minus 4, so our number up above here should change by a factor of minus 4. So we should have 1.67 times 10 to the third fibers. Next, if we do 1 millimeter squared, that's equal to 1 times 10 to the minus 6th. 1 times 10 to the minus 6th meters squared. We plug this in, not into E, it should be C. grams per meter squared times 1 times 10 to the minus 6 meters squared over 0.2 times 10 to the minus 3 grams per meter times 0.003 meters. And when we work through this, we're going to change by a factor of minus 7, so we'll end up with 1.67 times 10, which is equal to 16.7 fibers. So you can see as your area of inspection becomes smaller and smaller from 1 square meter, which is actually our whole paper sheet that we might initially consider, down to 1 square centimeter, down to 1 square millimeter. Overall, what happens? The number of fibers keeps decreasing and decreasing and decreasing. Alright, so let's summarize, because when we move to the next section, we're going to begin applying these techniques. So let's summarize. C sub D, keep making that too much of a hook, C bar sub D is a way for us to determine the mean number of fibers in an inspection area. So if we know the overall basis weight of the paper sheet, then we can determine the mean number of fibers within a given inspection area. You can actually see here there's a direct relationship between basis weight and center density. So if we wanted to calculate the basis weight knowing the center density, so if we know that center density, we multiply, gotta revise this, just rearrange this, and we can solve here on this side for x L sub f over area of inspection, and that will give us our overall basis weight. So we can determine the mean number of fibers within a given inspection area, and we can also determine here the relationship between basis weight and center density. So let me just foreshadow now very quickly to the next topic. And the next topic we're going to talk about is formation index. And that formation index, we're going to look at the variability. So instead of the overall, the average basis weight, we want to know BW sub L, the local basis weight. How would we determine that? We take this, we take X, L sub F, A sub I, multiply this by center density, not the average center density, but what the center density is for the individual points, and this will give us a local basis weight. Okay, so now we understand these relationships. Hopefully you understand what center density is at this point in time, how we use basis weight in different inspection areas or inspection sizes to determine the number of fibers within a given area. And also now at the end here, I've wrapped this up and I've pointed ahead to say we're going to start looking at the local basis weight and the local basis weight variability. That's all I have for right now, and we'll talk to you again soon. Thanks.